I'm a developer at Oracle in Broomfield, Colorado. We're in the old Sun campus there, if you're familiar with Colorado. There are a number of teams at Oracle using Spark. I'm just going to talk about my team. And you may have heard Oracle's changing to the cloud, or putting a big emphasis on cloud, but instead of doing, renting servers or renting storage, Oracle is focusing on software as a service, ready turnkey applications. And the application that we're deploying, hopefully later this summer, is called Big Data Prep. And it sucks in customer data from the cloud, you process, transform it, upload it back into the cloud. And this is what the main interaction screen looks like, a bunch of metadata in the main middle panel there. You can compose, whoops, I was looking for a laser. Nope, no laser. In the upper left corner, you compose a transform script that provides the steps, step by step, to do the transform. And to help the user compose that transform script, there's a bunch of recommendations in the lower left corner. And there's always the option to do manual composition of the transform script through some context menus. And then over in the right drawer, we have some file level profiles, column level profiles to help you do that transformation. So you've probably seen other applications like this that do similar sorts of things. So why would anyone care about this one from Oracle? Well, maybe you're an Oracle shop, or maybe you're interested in this big suite of cloud applications that Oracle is coming up with. But maybe you as developers might care attending this because the development's being done by this group of developers that originally came from Silver Creek Systems. So back in 2010, when Oracle was acquiring Sun, they were also acquiring this little tiny company in Colorado called Silver Creek Systems. They had 10 years under their belt of doing data quality, data cleansing, and a bunch of PhDs in natural language processing. So that's kind of the focus of Big Data Prep, or at least will be for 1.0. So this is a kind of an architecture of it. As you might imagine, there are a bunch of components and services. A lot of those components and services use Spark on the back end because the end user is sitting at a web page on this web app waiting for something to happen. And we don't want to make the user wait a long time, so we use Spark on the back end. One of these components is called the knowledge service. And the knowledge service has three responsibilities: discover, enrich, and standardize. So discover is, given a column of user data, like Michelin, Firestone, can we discover what the label should be for that column if we're getting this data from the user unlabeled? Enrich says, can we add another column related to that column, like headquarters location? And standardize is just a spell correction. So this talk is going to talk only about discover functionality within the knowledge service. So our problem statement here is we get some unlabeled data from the user on the left, and we want to end up there on the right with the label of tire manufacturer. And so the path we're going to take to get there is we're going to first look at our toolbox of available machine language tools, and we'll combine them in a straightforward manner and find that we end up in a dead end. And then we'll mix it up a little bit and finally end up at the right solution. So this slide is like the first day of Machine Learning 101. Hope you don't get too bored. So standard machine learning, supervised learning, you start with labeled data, and then you present your trained model with something it hasn't seen before, and it will spit out the label cat. Unsupervised learning is basically just like clustering. Why would you ever want to do unsupervised learning? Well, unlabeled data is a lot cheaper. You can get a lot more of it. You don't have to pay somebody to label it. You can scrape the web for it. So the downside of unsupervised learning is you present it with something it hasn't seen before. All it can say is class A or class 1, some cluster that it has clustered. Semi-supervised learning is the best of both worlds. So you feed it both labeled and unlabeled data. It does the clustering, and then you can propagate the labels within the cluster. And so the output with new data is a label. So to apply this semi-supervised learning to our problem, we need some unsupervised learning combined with a set of labels. So our set of labels is going to be Yago, and our unsupervised learning is going to be Word2Vec. So Yago is a research project out of Germany. They've taken Wikipedia, WordNet, GeoNames, and a bunch of other sources, crunched it, and came up with this enormous graph. Yago 3 is 90 gigabytes. That kind of attempts to be the sum of all human knowledge, but it's still not complete. So there's Word2Vec, which has even more data. This is a really powerful and interesting algorithm that's been getting a lot of traction. I think it was originally developed in 2011, but it was really popularized by Google at the end of 2013. So you give Word2Vec a bunch of sentences, and it picks out the words. And for each word, it assigns a vector, like a 300-column vector. 300 is a typical number. You can specify how many columns you want. And those correspond to a 300-dimensional vector space. Here I've only shown the first 3 dimensions. That's what I could draw. And the idea is that similar concepts are going to be close to each other in terms of that metric space. Okay, so we'll combine those two in a straightforward manner. And so when you have this huge list of words in Word2Vec, so like if you go to the Google Code Word2Vec page, you can download something that was trained off of Google News. It has a couple of million entries. So you have this couple million entries, each entry is a 300 position vector. The natural thing to do is you want to cluster it. That's going to give you clusters of common concepts. So you run it through k-means clustering. You get your clusters, the bubbles there at the bottom. And then you take your user data and you throw it against those bubbles and see which is the closest match. And then once you have that cluster that's the closest match, then you find the closest concept out of Yago that matches to Word2Vec. And the advantage of Yago is that it has, because it's human labeled, it has these is-a relationships. So, like Michelin is a tire. These genus-species relationships. And so that gives us the genus that we really want. Well, except in this case, Grand Prix is not a genus of the species Michelin. Something went wrong, and what went wrong is, I was using the Google News trained corpus, and it had a bunch of stories about the Grand Prix, and it really got sidetracked. So I just wanted to zoom in. What did I mean by find the closest set matched? There's a specific formula. It's called the Jacquard similarity. So if you have a set A coming from the user and a set B as your reference list, you just run it through this formula and it gives you a number back. So how can we mix this up to come up with something that works? So in this case, I didn't show where I was training Word2Vec. Assume Word2Vec is already trained. So at the lower left here, we're using an already trained Word2Vec model. And any implementation of Word2Vec, when I say model in machine learning, you're probably thinking, predict. Where's the predict function? Well, one of the functions of Word2Vec is called synonyms. You give your Word2Vec model a word and an integer like 10. Give me 10 synonyms. And so here we're using Word2Vec to augment our original user list. So it comes up with a more complete list. And this more complete list, when we throw it against Yago, can sort of wallpaper over some of the holes in the Yago data. And I actually show a hole in the Yago data right up there at the top, where the Yago data doesn't actually have Firestone as a tire manufacturer. The closest match it has is Harvey Samuel Firestone is a person. So by papering over it, we can get a closer match and come up with the right category of tire manufacturer. So just to get into some of the details here. So what is Yago? Well, Yago is this just gained a co-author, Robin East, so I want to shout out to him. He's probably asleep over in the UK, but the new cover didn't come out till Friday, so I didn't get into this presentation. Now, the reason GraphX wasn't a good fit is because this Yago data is almost relational. It's actually kind of hierarchical. And GraphX is better suited for sort of peer-to-peer node message passing. I could get actually all this processing. What I needed out of Yago, I could process it right on my laptop. I didn't need to use Spark or distribute. I just wrote a Scala program to process it right out. Anyway, the key thing that we're hinging off of on Yago is this RDF type. And that's kind of the ISA, I-S-A relationship. So Aristotle is a philosopher. And so there are lots of those. But Yago gives us even a little bit more, kind of some bonuses here. At the top here, it gives us alternative spellings, Aristotle versus Aristotle. And then we, at the bottom here, we get some kind of Russian nested dolls here. So Aristotle is not only a philosopher, he's also a scholar, an intellectual, and a person. And we can compose all these lists with greater subsets. Just some comments about so Yago 3 just came out in March 2015. Yago 2 came out in 2012. So it grew from 20 gigs to 90 gigs because they added multiple languages. And from that, we were able to project 400,000 lists in multiple languages. So how is Yago getting data out of Wikipedia? Well, it's nothing as high and mighty, pie in the sky as actually parsing all of the text. All it's really doing is scraping the stuff out of the info boxes, which is highly regularized. And if you've ever done any Wikipedia editing yourself, you know that sort of data is highly inconsistent, which is why we bring in Word2Vec to add the unsupervised component. The other place where Yago pulls data from Wikipedia are these categories. You may not have even noticed these things at the bottom, but Wikipedia editors pay attention to stuff like this. This is actually the important thing that we're getting out of Wikipedia, which is this ISA relationship. Okay, let us look at Word2Vec. So, Word2Vec is really powerful. So how does this Word2Vec model get trained? Where do these vectors come from? Well, the first thing you do is you pretend you're training a neural network. So you train up this neural network, and the goal of the neural network is to predict the next word in a sentence coming from your corpus. So, and ignoring stop words. So when we present this sentence, Aristotle and Socrates stipulated a model of citizenship. When we present Aristotle to the neural network, we want the neural network to reply back with Socrates. So the neural network is 1 hot, so Aristotle corresponds to the vector 1, 0, 0. When we present 1, 0, 0 to this neural network on the input side, we want to see the Socrates node on the output side have a high value. So we train up this neural network, it's all trained, and then we throw it away. So, but before we do that, we steal the edge weights out of the edges, and those become the values in our vector. And nobody's really sure how and why the details of this work, but it works really well. And no brief intro on Word2Vec would be complete without this slide, which came from one of their papers. In addition to this idea of word proximity, Word2Vec actually has some analogy capability where these are vectors, so you can subtract 2 vectors and get another vector, and then you can use that to draw these analogies. So man is to woman, is uncle is to aunt, and so forth. So the semi-supervised learning is not taking advantage of this analogy stuff. It's only taking advantage of the position stuff, but I didn't want you to be without this. All right, so the performance improvement. So the call for presentations for Spark Summit was due February 5th, and at that time, it was Spark 1.2. And so I looked at the source code for Word2Vec, and I saw this as being the key data structure, and you'll notice some things missing here, namely the letters R, D, and another D. And I thought, well, maybe there's a better way to do it. And I immediately thought of Ankur Dave's indexed RDD that you heard about if you were here a couple hours ago. The idea being that if you want to look up a word in your Word2Vec model, indexed RDD will take you there immediately. So indexed RDD, for those of you who aren't here, provides two main benefits. One is mutable data. You can modify data in your RDD. And the other is indexing. So a regular plain old RDD already has one layer of indexing. It has the partitioning key. But once you're in your node, then it has to do a linear scan. Like if you're doing a filter looking for one specific element in an RDD, it has to scan the whole thing once it gets to the node level. Indexed RDD kind of does a conceptual hash map down at the node level. But then Spark 1.3 came out, and it had a performance improvement, which is they implemented the matrix operations with a blast. And I said, oh, yeah, that actually makes more sense because for these fine synonyms, you have to multiply a vector times every of your 2 million vectors, and that's really where your performance bottleneck is and not on lookup. So that's in Spark 1.3, and I thought, well, of course, naturally, I start thinking about how can you improve that even further. So there are a couple of possibilities that I've thought of and not tested yet. One is you could just broadcast the whole model. So the Google News model is 2 gigs raw. I'm not sure how big it is in terms of JVM space. So that's on the line of something that of a size where you could broadcast that to every node. But perhaps even better than that is MLlib has built-in distributed matrix operations with BLAS, basic linear algebra system, very fast matrix operations down at the node level. And since Word2Vec is just doing simple matrix column multiplies, it would probably be extremely fast. There's one more embellishment here that I kind of skipped over that I'm going to cover now, which is instead of just throwing these literal strings directly against Yago, something could be misspelled slightly. So this is another embellishment. It comes from the natural language processing world is you break your word up into trigrams, and then you do a statistical match of those trigrams against your reference set of trigrams, so that way it can tolerate 1 or 2 missed letters. So that is the algorithm, and so where it fits into our application, I just wanted to be complete here. So, not all of our discovery is done through this knowledge service. It first goes through a layer of pattern matching, which is, just plain old, does this look like a URL? Does this look like a phone number? And things that don't pass the pattern match, the leftovers, that's what gets run through the knowledge service. And I have a list of references here. If you download the slides, you can follow the links for all this stuff. And that is it. So thank you.
Questions?
Do you mind keeping your references up there for a bit?
Oh, yes, sure.
Hi, this is a really nice talk. I had a question. How do you handle the words that you have not seen in the input data for Word2Vec before? Does it do a really good job at that as well?
I'm sorry, I didn't get that.
How do you, if you have data in your test set which the Word2Vec has never seen in the unsupervised training set before, is it still able to do a good job at that? With 2 million words, it's going to be in there somewhere. Actually, really the question is has Word2Vec been trained on the context that you're interested in? And if it hasn't seen that context, you're not going to get a good result. So really, in our application, the semi-supervised learning is kind of the last resort.
we're actually kind of hoping that we've seen that customer's data before so that we can get that data in context.
Come on this side.
Hi. What effect does modifying the dimension of your vector space have in Word2Vec?
So in machine learning terminology, these are basically latent variables. So with latent variables, you get into the issues of overfitting, right? If you have too many latent variables, then you're overfitting, and your model is not going to be as robust. If you have too few, then you're not accurately representing your data. You're not going to get as close a match. So.
Is there a way to learn like an optimal
Yeah, just the
dimension?
standard. I mean, obviously this n number of columns is a hyperparameter, so you can tune that in the conventional ways: trial and error, brute force, binary search, whatever.
Thank you.
Other questions?
Also, you mentioned these enhancements you're looking at for the Word2Vec implementation. Are these enhancements things that you've published as open source or contributed? Or?
When they are written, yes, I will be committing them back.
Iago is Wikipedia derived, right? And it's mostly about people, places. Like I'm dealing with e-commerce, large e-commerce site, and that sells pretty much everything. But I find that Wikipedia data is not a good. It's not really helpful. Would you recommend any other knowledge?
Yes,
bases?
yeah. Yeah, so there are geo-names, and like I said, we hope to rely on customer data and other, at this point, free sources. We hope to add some pay sources, since the software as a service is a commercial product, so in the future versions, there'll probably be commercial knowledge sources that you can draw in. But yeah, that's a good point.
Thank you, Michael. Thank you very much.